All right, Chapter 7 is talking about systems of equations and inequalities. Section 7.1 is describing 3 different types of linear equations that you might have. So we could end up with an independent system where we have 2 lines that intersect at one single point. We could have an inconsistent system where the 2 lines are parallel and they're never going to cross. Or we can have a dependent system where the lines are actually the same exact line. So every single point is going to be shared between those 2 equations. Here's an example. There's several different ways you can find what those points are. One example is by just checking an actual point. So in this case, it's asking whether or not the point 5,1 is a solution. So we can check that by plugging that in into our equations and seeing whether or not those are equal. So we've got x equals 5 plus 3 times 1 equals 8, and that's true. And then over here we've got 2 times 5 minus 9 equals 1, and that's also true. So the point 5,1 is a solution to this system of linear equations. Another way to solve it is to substitute for y. So in this case, we could take y equals x plus 1, plug it into our second equation, and find out what our value is for x. So we've got y equals -2, and now we're going to plug in our y value. Sorry, let me go backwards there. There we go. So we're going to substitute y for this one. So we've got x plus 1 equals -2x minus 8. And let's start to solve for this. So thinking ahead, we would like to get a positive x. So let's go ahead and add 2x to both sides. It's going to give us 3x, and then we can subtract 1 from both sides. So 3x equals -9, or x equals -3. So there's our -3, and now we can take x equals -3, plug it back into our equation, and solve for y. So if x equals -3 plus 1, then y equals 2. -2, which is what we have here. So that's a y substitution method. And this next one is the addition method. So if you were to add up these equations, you want to eliminate one of the variables. So if we add up these equations, we can eliminate the x right away. So let's take our equations, write them on top of each other, and then we're going to add them. So x plus a -x is going to give us 0. A 2y plus a y is going to give us 3y. And a -1 plus the 3 is going to give us 2. So we've got y equals 2/3. And now we can take our y equals 2/3 and plug it back into one of the equations here. And I usually like to look ahead and see which one makes the most sense to plug it into. In this case, it looks like this one's already a positive x, so that seems easier to me. So let's do x plus 2 times 2/3 equals -1. So we've got x plus 4/3 equals -1 minus 4/3. So x equals 3/3 minus 4/3, so -7/3. So there's our -7/3 and our 2/3. So that was the addition method. Here's another addition method where we are going to have to manipulate the equation just a little bit, because here we've got 3x plus 5y equals -11. We want to multiply one of the equations by something so that we can actually eliminate a variable. So if we have a 3x here, then what we'd want to do is go ahead and multiply this by a -3, multiply the whole equation by that. So that way when we add 3x, we're going to subtract 3x, and we're going to be able to eliminate that x variable. So let's just distribute this negative 3 through to that equation. So it's going to give us negative 3x plus 6y equals negative 33. And now we can add that. That's going to give us 0x. We've got 11y equals negative 11 plus a negative 33 is going to be a negative 44. Divide that by 11. So y equals negative 4. You can see that right there. And then we'll take this value of y equals negative 4 and plug it into one of these equations. Either one looks fine to me. Let's do this one. So we've got x minus 2 times negative 4 equals 11. Or x equals, this is going to be positive 8. So minus 8, 11, minus 8. It's going to give us x equals 3. So there's our x equals 3 right there. This one is another example, only this time we have to actually multiply both because we can't multiply one equation. We can't multiply anything by the 2 to turn it into a 5. We can't multiply the 5 by anything to turn it into 2. So we want to take the least common multiple, which will be 10. So that means that we have to multiply this by 5. And then we'll multiply this by 2, but we want this to be a negative 2. So that when we add it, it'll eliminate that variable. So let's go ahead and distribute that through. That's going to give us 10x plus 15y equals negative, sorry, I'm going to have to get my calculator. I didn't have this in my notes yet. 16 times 5 is 80. And then let's distribute the negative 2 through the other equation. That's going to give us negative 10x plus 20y equals negative 60. And now we can add those. So you can see we got rid of our x variable. We're going to end up with 35y and negative 140. And then that divided by 35 is going to be 4. So y equals negative 4, which we have here. And now we can substitute y equals negative 4 into one of these equations. They both seem just as easy. I'm going to pick this one. So we've got 5x minus 10 times negative 4 equals 30. 5x plus 40 equals 30 minus 40. 5x equals negative 10 divided by 5. So x equals negative 2. There you go. Here's an example of an inconsistent system. There you go. We're inconsistent here because we don't have any shared points. And we can tell that it's inconsistent because we're looking at our slope. If you remember, parallel lines have the same slope. So here we have a negative half x slope, and here we have a negative half x slope. If you're looking at these without graphing it, what you want to pay attention to then, after you determine that it has the same slope, is whether or not it has the same constant. So in this case, we have 9 halves, and in the other case, we have 13 halves. So those are not the same line. If they had the same constant, then they would be the same line, in which case it would be a dependent system. So you can see here, it's not quite as obvious because you've got a 3x here and a x here. But if we were to solve this for y, you'd be able to tell a little bit easier. So let's go ahead and do that. We've got 3y equals negative x plus 2, or y equals negative x plus 2/3. And then here we've got 9y equals negative 3x plus 6 divided by 9. So y equals negative x over 3 plus 2/3. So you can see that we've got the same exact slope and the same exact constant. So we've got a negative third x for the slope and a plus 2/3 for the constant. So this system is dependent. They share all the same points because they're the same exact line. Now, one of the things that's going to be most beneficial in doing this is finding your break-even point. So in business, if you've got any sort of situation where you have expenses, profit, revenues, costs, you're going to have a break-even point. You want to know where that is. So if this is your equation for your revenue, and this is your equation for your cost, you want to know when your cost and your revenue are equal to each other. So that's considered your break-even point. So in this example, we have our system that is independent. So it's meeting in one single location, and that location is called the break-even point. So here's just another example where everything from here is going to be your profit because you've passed your break-even point now, and now you're getting into the profit zone. Here's an example where the break-even point is at the 0 mark because up until then, you've been running a deficit. So you've been running in negative $35,000, and you begin to actually break even once you hit your 50,000 quantity mark. That's your break-even point in this example. So from here, we're going to start looking at, we've been looking at systems of just 2 equations or inequalities. Now we're going to start looking at 3. So visually, this is what happens when you can see the three different situations intersecting. So you've got these 3 planes, and they can intersect in such a way that they only intersect at one single point, or they can intersect at multiple points along those planes. So in this last case, we have infinite solutions. In the first case, we only have a single solution. Here's some more examples of what that could look like if you were talking about planes. So you've got your 3 variables now, your x, y, and z, and you can have intersections between just two of the planes. Here you also have some intersections of 2 planes. And then here, all the planes are parallel, and they aren't going to touch at all. The gaps don't necessarily have to be the same. But either way, they're parallel, so they're not going to intersect. And this is just back to our example of intersecting at one single point. And again, this is your x, y, and z now. And here's an example where the 2 equations are actually the same. They're the same plane. So these are going to have infinitely many solutions where they intersect, where the whole plane actually intersects itself. These are just some examples of if you were intersecting a line with a parabola, some situations that you could get where there's no solution at all because they don't touch, where you can have one solution because they are just adjacent to each other and they just hit at that one single point. And then the last one where the line intersects the parabola completely, so you would end up getting 2 points somewhere on that parabola line. And here's an example where we've got those 2 points. So just like we did before, you can substitute to find what those values are. We could go ahead and do that really quickly. Since this is already set up for y equals something, I'm going to plug that into here and solve for x. So that's going to give us x minus x squared plus 1 equals negative 1. So we've got x minus x squared minus 1 equals negative 1. So we've got one point where they're equal to each other. So we've got the case where a number squared equals x. So we've got an x equals 1. And another example where x squared could equal x is at x equals 0. So 0 squared would still equal 0. And that's it. So next we could do is go ahead and substitute these back into one of the equations. So we've got y equals 1 squared plus 1. It's going to give us 2. So we'll have a point 1, 2. And then let's substitute x equals 0. So if we have a 0 here, that's going to give us just 1. So we've got a point, another point at 0, 1. So you can see that both of those points right there. Here's another example where you have a line intersecting a circle. The different types of situations you could have. You could have no solutions at all because they don't touch. You could have one single solution where it's tangent to it, or you could have two solutions where it completely intersects the circle. And here's an example of where that could happen. I'm not going to go through this one, but it's the same idea again. So you could go ahead and plug in y. Since this one's already nice and neatly set to y equals something, you'll just plug that into this equation, solve for x, and then plug in your x to find out your y value. Here's an example if we had a circle and an ellipse. We could have no solution at all because it's either completely inside or it's outside somewhere where it's far enough away from the circle that it's not going to touch. You could have your tangent ellipse where you hit one single point. You could have your intersection where you've got 2 points. You could also have a situation where you end up with 3 points like this, where one is tangent and then the other two are just completely intersecting the circumference of the circle. And then the your 4 solutions where your ellipse and your circle completely overlap each other at all 4 points. So here's an example of that, and I actually don't have the equation, but you can check this out in your book too, and just follow along with the points here to show that you'll end up with your 5, your positive 5 for x is going to give you a -1 and a positive 1, and then your -5 is going to give you a positive 1 and a -1. Okay, now we're going to start talking about inequalities. So these ones are parabolas, and we're looking at the inequalities for these. So this one is saying that we want the y values that are greater than that line or that parabola. So here's our parabola. Because it's saying it wants things that are greater than, we want all of this. These are the y values that are greater than this line. And then it's saying just greater than, not equal to. So in this case, we're going to go ahead and make these dashed lines because it's not including the points on that line. It's including everything that's greater than that line. The next one, you can see it says y greater than or equal to that. So we will keep a solid line in this case. And we want all the values that are greater. This next one, we want y values that are less than. So we want the y values that are going to -infinity. And because it's not saying equal to, we want to keep this line dashed. And the last example is saying y less than or equal to. So we'll keep the solid line, and we want all the values that are below that line. One of the ways to check this, I know a lot of people get confused as to which direction. You can grab a point and check it. So let's say you're going to take here, you're going to take the point 0, 1. Go ahead and plug that in and see whether or not it's true. If it's not true, then that's not included as part of the solution set. So you'll know that you're going to shade the other region. If we plugged in, say, 0, -5, the statement would be true. So we would know that that's part of the solution set. So that's part of where we're going to shade. Here's another example. We've got y greater than x squared plus 1. So if you remember, x squared is your parabola, your basic toolkit parabola. But plus 1 shifts it up 1. And then y greater than. So we want all the y values that are greater than that line. And because it doesn't say greater than or equal to, we want to keep that line dashed. So that's how we would graph something to represent that inequality. And then we get even trickier, and now we want to know what the solution sets are for a system of inequalities. So we would graph both of our parabolas, and we want to know where they intersect. So the way these are written, it's a little bit hard to visualize it. So let's rewrite this. Let's take the first one. We've got x squared minus y is less than or equal to 0. I think it's going to be easier to go ahead and shift the y over. So it's going to give us x squared. Because we're shifting the negative sign, we want to switch our signs. And that's going to, and then drop the negative. So it's going to give us y. So we've got y less than or equal to x squared. Sorry about that. I made a mistake there. That's not, we're not switching our signs yet because here we're just adding a y. It was a negative y here, so we're going to add y and add y. So we're actually not switching the sign yet. So it's going to give us y greater than x squared. So we've got our x squared here, and we want the y values that are going this way. And then let's do the next one. The next one we've got y less than or equal to negative 2x squared plus 12. So we've got a negative 2x squared, so this is this one. And we want the y values that are less than or equal to that, so it's going to be a solid line, and we want everything going down. So now this region inside where they both collide is our solution set.